The usual way for plotting some function of a single variable x is to take a sequence of values for x, plug them into the function, and plot the resulting numbers against the numbers we just plugged in. This most often yields a single curve, although it isn't so hard to imagine a function that results in multiple curves. But let's stick to functions of single curves for this video. We might be tempted to think that this curve shows us all the values that this function can take. After all, if we take a function like x squared minus x plus 1, no matter what we plug in, the output will be a positive number greater or at most equal to 1, lying somewhere on this curve. But what you also might remember from high school algebra is that functions like x squared minus x plus 1 always have two values of x that when plugged in, give back a 0. These are easy to see for x squared minus x minus 1. It's just the points where the curve crosses the x-axis. But what about our x squared minus x plus 1? The curve lies entirely above the x-axis, so there are no values of x that give 0. Or are there? Yes, there are. And there's actually an entire second curve that reveals the fact that x squared minus x plus 1 can give negative numbers. Welcome to the lovely world of phantom graphs. To understand the graph you are looking at, let's start with the quadratic formula. You probably memorized it in high school and then promptly forgot it, so just as a little reminder, it's the formula that gives us the roots of any quadratic function. For our function, the resulting roots are these two numbers. Both include the square root of minus 1, and that's why we cannot see them on our original graph. They are complex numbers, part real, part imaginary, and as such, they can only be seen in a complex plane. That's this graph, where along the horizontal axis we plot real numbers, like 1, 2, and 3, and along the vertical, imaginary numbers. Numbers anywhere else are complex, so the two roots of our graph are here. Now, let's draw a y-axis, which just like before, we'll use to plot the values of our function. The curve that we started with is here. Its inputs are the real numbers along the real axis, and its outputs are the real numbers along the y-axis. But there is also a special sequence of complex numbers that when plugged into our function doesn't give back a complex number, but a real one. This sequence is the phantom curve of our function, and when plotted, it reveals the complex roots we found earlier. What it also shows is that numbers like 0.5 plus 2i or 0.5 minus 1.5i return a negative number. So even a function like x squared minus x plus 1 that is seemingly strictly positive can output negative numbers. We just had to stretch our imagination a bit. Pun intended. This of course works for polynomials of any degree. Here's for example a cubic function and its phantom curves. And here's a quartic one. How we derive the equations for these phantom curves is quite simple. You take the original function and instead of a real variable x, you plug in a complex variable x plus zi. You carry out the necessary algebra and find that the result again has a real and an imaginary part. To find the equation of the phantom curve, you set the imaginary part to 0 and solve for x in terms of z. Plug this back to the real part of the result we obtained earlier, and voila! This is the equation for your phantom curve. And of course, phantom curves don't exist just for the polynomials. But that's a topic for another video. If you enjoyed this one, there are links to interactive plots where you can play with phantom curves in the description below. Like, comment, subscribe, have fun, and see you in the next one.